Yeah, hello and welcome back to our magic string theory module. Today is already our 9th lecture, and I plan to finish with part 5, where we look at string theory from the space-time perspective and work out its particle spectrum. And time permitting, I will then start with part 6. Part 6 is kind of open-ended. And next time I will then teach as much of this part number 6 as we have time for. I have already put the slides for part 6 online, and I've also pasted the third and last example sheet. It's a rather short one, and it should make sense after we have completed today's lectures. What else? No, I think that is what I wanted to say organizatorically. So I think last time we ended up somewhere in the middle of understanding the mass spectrum of the closed string. So let's rewind a little bit. I've brought up here a table where we can see the lowest mass eigenstate of the closed strings as they appear once we have imposed the L0 constraints, which give us the mass formula and the level matching. We start out at level 0 with the scalar tachyon. As I mentioned, as soon as we enhance or augment our string theory to contain matter, that is fermions, these tachyons go away. And the spectrum then looks like the one of the bosonic string from the 0 mass level upwards. So we don't worry much about this tachyonic scalar further. And then at level 0, we have a second rank tensor, and we were in the middle of analyzing this. And then if we go up, we get massive states and ever more possibilities of building Lorentz tensors out of our oscillators. Good, we commented on the tachyon. Here, just to repeat this again, we now look at we start out by looking at the most general massless closed string state, which looks like this. Zeta mu nu is a polarization tensor, and it's now a general rank 2 tensor. We have already imposed the L0 constraints. The constraints from L2, L3, and so on don't give conditions, as you can check, but the L1 operators give us conditions, and these conditions say that if we contract the polarization tensor with the momentum vector, we get 0. Our next step was to decompose the polarization tensor in its symmetric and antisymmetric part. This is what we can and should do because these don't mix under Lorentz transformation. And now we can look at them separately. The photon has already taught us that in general, we will have physical non-zero states which correspond to gauge symmetries. It's important to identify them. And for the symmetric part, the null states takes the form of a symmetric bivector, which is formed out of the momentum, and a second vector, which must be orthogonal to it. Now, to proceed, we observe that the symmetric tensor is still reducible under Lorentz transformations because the Minkowski metric is a Lorentz invariant tensor. Therefore, we can form the trace of a symmetric tensor and obtain a Lorentz scalar, which we have to separate out. And I gave you explicit formulas how this can be done upon choosing an auxiliary light-like vector, which is determined by its scale, essentially by its scalar product with the momentum vector. And then we get this explicit decomposition into traceless part and pure trace part. We briefly mentioned that the trace part is a physical state. It's not null. It's in particular it's gauge invariant, and therefore it's a physical scalar field called the dilaton. And I will come back to the dilaton a bit later. Now, the traceless part, let's analyze this. We know it must be transversal, and we can be explicit about how this decomposes into gauge degrees of freedom and physical degrees of freedom if we pick an explicit momentum vector, like the standard one, where a plane wave, or if you prefer a particle, is propagating along a particular axis. And we can write out this condition, and we get certain constraints between the components. We already have this as a symmetric, and then we arrived at formula number 9, which we can now decompose because we know that the spurious part takes the form of a symmetric bivector. This is property. We can now explicitly pull this apart. And the transverse part then corresponds to a symmetric in traceless d-2 times d-2 matrix, which sits in the middle. And then on the outer rim of this matrix, if you like, we have certain parameters, d-1 independent parameters, which are our gauge degrees of freedom. So it's a very explicit decomposition. And here's the counting. So we can now break down the components into unphysical ones. These are those which are eliminated by the constraints. Spurious, these are the states which are physical but have zero norm. And then what remains are the physical, or more precisely the inequivalent physical states, or the physical states modulo gauge transformations. There's a short explanation here how the counting goes. I'll leave this to your own reading, and I will in particular give you the same thing for the B field as something that you also should think about yourselves. But the upshot is we end up with 1/2 d-2 times d-1 minus 1 independent degrees of freedom. And I claim that this matches with the physical degrees of freedom that a graviton has in dimension capital D. In particular, in D equals 4, we have 2 independent physical degrees of freedom. And here we can make the connection more explicit. In 4 dimensions, the residual Lorentz symmetry that we have after picking a momentum vector is SO2. And this acts on the polarization tensor, or on the 2x2 block of the polarization tensor, which contains the physical degrees of freedom. This is symmetric traces 2x2 tensor. This transforms as a symmetric tensor onto the Lorentz group. I've written this out here in matrix notation. And as for the photon, one can go to a circular polarization basis, which diagonalizes this 2x2 matrix. And then we find 2 eigenstates. And the difference to the photon is they transform with different powers of e to the I5. Now for the photon, it was the first power, or the first negative power, hence helicity ±1 for a photon. But for these states, we have helicity ±2. So loosely speaking, this is a massless spin 2 particle. And that's the only known consistent interaction for such a particle is gravity. We can also check this is consistent with group theoretical reasoning. Here we have to take our Lorentz tensor and decompose it in 2 steps using branching rules into representations of the little group, which is the transverse rotation group for massless states. And then you see the same counting, and you can also see in what kinds of representations the physical spurious and unphysical degrees of freedom fall. In 4 dimensions, the situation is simplified by the little group being abelian, and therefore our 9-dimensional symmetric traceless tensor just decomposes into 9 scalars, and 2 of them are physical. These are those with the helicity ±2, and the remaining 1 are pure gauge or unphysical. Now, of course, graviton has not only kinematics but also dynamics. But just to see that how this arises from the field theory perspective, the way you assign a particle-like excitation to gravity is by linearization of the Riemann-Einstein-Hilbert action, or equivalently of the vacuum-Einstein equation. That's the universal principle. If you have a set of field equations and want to know the particle contents, and you find a vacuum solution and expand to it, and the quadratic piece, or at the level of the field equation, the linear piece, tells you what kind of fluctuation you have, what kind of representation of the Poincare group it corresponds to, and that assigns mass and spin. Here the way to do it is to realize that the ground state is Minkowski spacetime, is a Minkowski metric, so one decomposes then the spacetime metric into a background vacuum solution, Minkowski spacetime, and then fluctuations around. Here I've also factored in a factor kappa of the gravitational coupling. And then one expands the Einstein equations. And if we expand the vacuum Einstein equations to leading order, then we see that this fluctuation satisfies the wave equation in each component. Yeah, provided that, like for the photon, we impose certain gauge conditions to simplify. So there's an analog of the Lorentz gauge for gravity. It's variably called Einstein or de Donde or Weil gauge, and has probably 2 or 3 other names too. But what these extra gauge conditions do is they remove those degrees of freedom which are not helicity plus minus 2, or in general dimension which do not belong to the symmetric traceless tensor of the little group. So kinematically, a graviton is a massless traceless symmetric tensor field, or loosely speaking, in 4 dimensions, a massless spin-2 field. And yeah, there are statements in the literature that this is the only consistent way a massless spin-2 particle can interact, that it uniquely leads to gravity up to higher derivative terms. But from time to time, you will find research articles posted on the archive, which then look at subtleties of this. But more or less, the folklore is that general relativity is the unique, and it's certainly the minimal choice for the most natural choice for an interacting massless spin-2 particle. And it pops out of string theory in this way. In this course, at least, we see this at the kinematical level. Now, briefly to the antisymmetric part. I will be rather short and leave it for you to go over it and do your own thinking. So these are the conditions that we have. Null states are now antisymmetric bivectors, again with the condition that momentum and the auxiliary vector, or the second vector zeta, which forms the bivector, are orthogonal. And here are our residual gauge transformations. I claim that this is a breakdown into physical, spurious, or gauge, and unphysical states. The numbers are a bit different from the symmetric part, and I would like to encourage you to think about this. The corresponding antisymmetric tensor state is variably known as a Calpe-Ramond field, or B field. And in 4 dimensions, one can equivalently transform it into a scalar field, which is called the universal stringy axion. And I would like to tell you a little bit more about this universal stringy axion. If you have encountered field theory before, nobody will, in a typical beginner's talk, have talked about massless antisymmetric rank 2 tensor fields. And the reason is that these fields can be equivalently thought as scalars. More precisely, these are axion-like scalars, which means that they only appear with a derivative in front and not the field itself. That means that the theory has a shift symmetry, meaning that this is a scalar field which you can shift by a constant and still solve the equations of motion. Let us illustrate this equivalence between tensor field and scalar field in the free theory in 4 dimensions. Starting point is a Maxwell-like Lagrangian if we take a completely antisymmetric rank 3 tensor. And this is interpreted as a field strength, which has an associate potential, which is an antisymmetric rank 2 tensor and formed according to this formula. If you take into account that B is completely antisymmetric, this formula is again a generalized curl, or for those who know differential forms, an exterior derivative. Now, given this Lagrangian, we can then get the Euler-Lagrange equations, which tell us that the divergence of H is equals to zero because we did not introduce any interactions. And then there are again Bianchi identities which are needed in order that H can be written in terms of B, and that is this contraction with the epsilon tensor. Now, what is the idea of dualization? We take the three-form field strength and contract it with the epsilon tensor, the totally antisymmetric tensor, and we get a field strength which is a vector. You can reverse this formula, of course. If you substitute this in, then the divergence and curl formula, or Euler-Lagrange equation and Bianchi identity, swap their roles. What was previously the Euler-Lagrange equation now looks like a Bianchi identity, and what was the Bianchi identity looks like a field equation. And that motivates us to say, okay, since the vector field F mu has this Bianchi identity, which allows us to write it in terms of a scalar potential, we introduce this in such a way. We interpret F mu as a field strength and phi as a potential, or scalar potential for this vector field strength. And then, indeed, the field equation that we have for phi is a massless Klein-Gordon equation with a standard Lagrangian for a massless scalar field. What has happened to the gauge symmetry of the field B, which actually I think I didn't mention, but if you look at this formula, what you can do here, this mu nu, you can change it by the curl of a vector field. This is what, sorry, I didn't write it explicitly. This is what I mean by the gauge invariance that this field B has. And if you make this transformation, the field strength H does not change. And then a natural question is, what does this gauge symmetry of the B field translate into? And it translates into a shift symmetry for the scalar field phi. And therefore, this is called an axion, or an axion-like scalar field. But here's a remark for those who would like to do this in a Lagrangian framework. So you need to do a little bit care if you implement the duality transformation with a Lagrangian. I did it here directly for the field equations. If you want to do it with a Lagrangian, you need first to promote the Bianchi identity into a field equation, and then you can dualize. If you just substitute back what we got from changing the field equations, then you would flip the sign of your Lagrangian, which you don't want, because you want to keep the right sign for kinetic energy. Okay, that's a side remark. Leave it to you to look into this. Another side remark, we can do the same dualization game in 4 dimensions with a second rank field, antisymmetric tensor field, for example, the electromagnetic field strength. In this case, going from a rank 2 tensor to another rank 2 tensor, so called Hodge dual, and it has the effect of exchanging electric and magnetic components in the field strength tensor. Therefore, this is then called electric magnetic duality. So the duality between H and phi is also, or yeah, between B and phi is a kind of generalized version of electric magnetic duality, if you like. And I hope next time to have some time to talk about T duality in string theory. This kind of symmetry can also be viewed as a version of electric magnetic duality, but performed on the world sheet, not in space-time. Now, remember that in our conformal field theory part, we stress that there's a state operator correspondence. For each state in the Hilbert space, we have a corresponding vertex operator, which by insertion on the world sheet creates the state. And we already know from this part how the vertex operators for tachyon look like. It's a normal ordered exponential. And for a massless closed string state, it's the exponential dressed up with the derivatives of x, and now we build in also the polarization tensor to get this operator. What do the Virasoro constraints tell us about the vertex operators? If we impose the Virasoro constraints on the states, then this implies that the physical vertex operators have conformal weight 1, 1. And this is a property that we certainly want to have, because as I explained, our idea for defining probability amplitudes between states is that we take correlation functions in the worldsheet conformal field theory between the vertex operators and then integrate them over the worldsheet. But for this integral to be invariant, to have weight 0, 0, we need to cancel the scaling properties of the variables we integrate over, and therefore vertex operators for physical states must have conformal weight 1, 1. And this logic can be reversed. We can say a vertex operator is physical if and only if it has weight 1, 1, which means that we have these OPEs between the energy momentum tensor and the vertex operators. And if you now take any of these vertex operators, for example, the tachyon vertex operator, which I will give you as an exercise, or if you want to do a bit more work, take this one here for the graviton state, or graviton, dilaton, and antisymmetric tensor state, then you can show that by imposing that the OPE takes this form here, you get the same conditions on the momenta and polarizations as from the Virasoro constraints. By the way, what you have to check explicitly is not only that the coefficients for the second order pole is the correct one, that the coefficient for the first order pole is the correct one, but if you look at the massless vertex operator for the massless states, in principle, this would also have higher order poles, and by imposing that these higher order poles have 0 coefficients, you get part of the physical state conditions. Good. Now I wanted to say something about the string coupling constant and its relation to the dilaton. So let's first talk visually about the string vertex. My new device seems to work. So I now got one of these document cameras, which are really quite useful. So what we see here is, let's consider a theory considering of closed strings. Then there's only one kind of vertex that we can draw, namely a process where either one string splits into two or two strings fuse into one. And the distinguished property compared to point particle theories is the following. If I think about point particles, and the propagation is represented by lines and interactions by vertices. But vertices are distinguished points. And if I have really a graph where lines can split, then this is not a one-dimensional manifold. It's a more general object, a graph. However, for strings, the worldsheet always looks locally the same. It's a two-dimensional manifold, and we can describe string interactions without going out of this category of manifolds. A very practical consequence is the following. And if I work with point particles, then I have to draw a different kind of line for every kind of particle. And since the interaction points are these distinct vertices, I can free to specify a different coupling constant for each kind of vertex that I can draw. There's a proliferation of possible interactions and coupling constants that I can have. But for a string, I don't have this kind of freedom. There's just one vertex, and I can introduce one coupling constant. By the way, this also persists if I have theories which have open strings. You can have series of closed and open strings, but it turns out that the open string coupling constant is then uniquely related to the closed string constant. So any kind of string theory that you draw, irrespective of whether closed, open, oriented, non-oriented, will end up with only a single coupling constant. Now, what will this coupling constant be? Instead of the generic G, I can observe here that among my closed string states is certainly the graviton. So this string vertex will, in particular, in some limit, have to reproduce the three graviton vertex underlying the interactions of gravity. And therefore, this coupling constant must be related to the gravitational coupling constant, which I will call kappa. So back to these slides. Now, what is special about the gravitational coupling constant is that if you are above 2 dimensions, it's dimensionful, and it has negative mass dimensions. If you had a course in quantum field theory, you will remember that this means that it is non-renormalizable by power counting. So if you set up such a theory in the context of perturbative quantum field theory, then you need infinitely many independent normalization conditions to get rid of all the divergences in the theory. It cannot be predictive if you want to go to arbitrary energies. So, but we want here to solve or to discuss a somewhat simpler problem. So, well, another important problem, let me phrase it this way, we have a dimensional gravitational coupling constant. Now we can express it in terms of either mass or length. H bar equals C equals 1 as usual. I have, of course, a choice. I can use other dimensional full constant. I can use Newton's constant, which is essentially the square of kappa, or I can convert this into a mass unit called the Planck mass, or a length unit called the Planck length. So that this dimensional coupling gives me a fundamental mass or length scale. But string theory already has a fundamental dimensionful constant, which we either take to be the string tension, which is in front of the vertical action, or the so-called Regge slope, which has dimension of an area. And if you like, we can convert this again into a mass or length unit. But now we have seem to have two different fundamental mass or length scales, and we wonder what this is going to tell us. If this were really two independent fundamental mass scales, then the ratio would be a free parameter which could label different inequivalent theories. So then we would have infinitely many different string theories depending how these two scales are related. But this is not so for the following reason. Here I have to cite something that comes out if you really analyze interactions. More precisely, if you analyze interactions between gravitons and dilatons in string theory, you can rewrite the result in terms of an effective action for the graviton or metric and the dilaton, and up to higher derivative terms, it takes the form that we have indicated here. So you will see here that there is a Regge scalar, so it is a generalization of the Einstein-Hilbert action. It has a term, kinetic term for the dilaton, but it also has, because I've written it in a particular way, an overall exponential of the dilaton in front here. And this has some importance. Now we first note that the equations of motion can certainly be solved by taking the metric to be the Flat-Minkowski metric, and by taking the dilaton to be constant, but there's no condition which tells us which constant value for the dilaton we have to choose, because there's no potential for it. In other words, the vacuum expectation value of the dilaton is a free parameter, and then one says that this dilaton is a so-called modulus, which labels different vacuum or ground states of the theory. How does this relate to our issue with different fundamental scales? Now, if you look here, how this dilaton exponential is paired up with a gravitational coupling constant in front, then you can see that a shift in constant shift of the dilaton, which we can interpret as changing its vacuum expectation value, is equivalent to rescaling the coupling constant kappa. And you see here all other terms in the action only contain derivatives of phi, so constant shift will not have any effect here. And that means that we have in string theory one single dimensionful constant, which we could take either alpha prime or kappa. And that has a whole moduli space of ground states which are parametrized by the dilaton. Another way of, if one looks at more complicated space-times in which a string propagates, and there might be further scalar fields with undetermined vacuum expectation values, which also are called moduli, and I hope you will see an example next time. Put differently, what the dilaton vacuum expectation value parameterizes is the ratio between kappa and alpha prime, or if you like, the ratio of the string versus the Planck scale expressed either in terms of masses or lengths. What one then often does is one eliminates kappa, takes alpha prime as a fundamental length scale, And for the vertices, where one has replaced kappa, one is then left with a dimensionless string coupling constant, which is the dilaton exponential. By the way, here I've not cared for numerical factors. If you look this up in the literature, these formulas will necessarily contain some numerical factors, which are important if you want to compute certain things explicitly, but which are not so important if you just aim for understanding what is going on with these scales. Now let's wrap up the covariant quantization program. The main issue with our covariant quantization program is that the price for having manifest Lorentz covariance is that we need to talk about unitarity. And unitarity means two things. The thing which we have immediate access to is that we can look at our Hilbert space, which comes out if we quotient the physical states by the gauge transformations. And on this space, we must have a positive definite scalar product. But in a full interacting theory, that also means something more. And if you then look at the S matrix, which is the asymptotic time evolution operator between an in and outgoing states, then this must be unitary. So that is a fundamental requirement in quantum mechanics. Time evolution is unitary. The first condition, that we have a positive definite scalar product, can be shown to imply that there's an upper bound for the dimension d, which is 26, and an upper bound for the shift in the vacuum energy, which is A. Because if these inequalities are violated, you can explicitly construct some negative norm states which are physical and which are called ghosts. They're different from the so-called Fadeev-Popov ghosts. I must say Fadeev-Popov ghosts are useful if norm ghosts are bad, so to speak, bad ghosts, which destroy the consistency of our theory because we don't have the standard quantum mechanical setup. Now, at the level of the free theory, one cannot go further than this, because if I have a theory which is unitary for d equals 26, then I could just trivially truncate it to any lower dimensions, and this would not introduce any new negative norm states, because I'm just making the spectrum smaller. However, if one then looks at internal states in loop diagrams, one finds if d is different from 26 and a is different from 1, then these negative norm states reoccur as internal states in loop diagrams. And since if a state appears as an internal state in a loop diagram, then it should also exist as an external state. This again spoils the unitarity of the S matrix. So that's and one ends up with d equals 26, a equals to 1. So you see in the covariant framework, this is a rather hard result to get. But I will indicate in the rest of this session how one can really fully derive the same result in a non-covariant quantization scheme. And this will also be useful for us to work with work out the massive spectrum. Right? We'll also want to have, so far, mostly discussed the massive spectrum, because there were all these important fields, the photon, dilaton, the graviton, and so on. But full understanding of string theory requires to master the massive spectrum, its representation contents in terms of mass and spin / helicity. And for this, the so-called light cone gauge is also very useful. So I will introduce this. So light cone gauge. So first, we just introduce a new parametrization, which is similar to the light cone coordinates that we had on the worldsheet. So we pick one of the space coordinates and pair it together with the time coordinates to form light cone coordinates. Compared to what we did on the worldsheet, there's a conventional factor 1 over square root of 2 here. And of course, in space-time, we will then be left with additional space-like coordinates, which are labeled xi, d minus 2 of them, and these are then the transverse coordinates, transverse to the light cone spanned by x plus and x minus. Good. We have already imposed the conformal gauge, and our residual reparametrizations are all reparameterizations which do not mix sigma plus or sigma minus, or equivalently, we can write it out with sigma 0 and sigma 1, and then we see that the new sigma 0 tilde and sigma 1 tilde need to satisfy the wave equation with respect to the old coordinates. Now, the idea in the light cone gauge is now that before we quantize the theory, we use up this remaining freedom to impose a condition. And the condition is that we say that the x plus component of the string should look like a particle, so no oscillator. So equivalently, we can say all alpha plus oscillators are set equal to 0. And what we can do then in this gauge is we can solve explicitly before quantizing all our constraints Lm equals to 0. And this just gives us enough to compute the alpha minuses in terms of the transverse oscillators. So each alpha minus is now not an independent object, but an infinite quadratic sum in transverse oscillators. And these are then truly independent physical degrees of freedom. The gauge is fixed completely, except that for a closed string, we can still shift sigma 1 by a constant, but this just means that on a closed string, there's no preferred origin. The price that we pay is that we have lost manifest Lorentz invariance. Now we have thrown out the alpha pluses, and the alpha minuses are also now special, so that is not covariant. But if we now perform quantization in such a light cone parameterization, it is manifestly unitary. I've written down here what the commutators are that you then impose. The first two set is equivalent to the quantization of a particle in the light cone gauge, and this particle we can think of as a center of mass. But more importantly for us is what happens with the oscillators. And for the oscillators, we are just left with the transverse ones. And then, of course, we don't have a Minkowski eta here anymore. We get a Kronecker delta, which is positive definite. And this is what makes the difference with having a manifestly unitary quantization scheme. Again, there's a price, because after quantization, we have to check Lorentz invariance carefully, because as we have seen, there might be ordering ambiguities with our operators, and something might not work in the same way as in the classical theory. So we can't trust Lorentz invariance. We have to check it in the quantum theory. But before doing this, let's talk a little bit about states in the light cone gauge, because what is nice about the light cone gauge is that all the states that we now write down in terms of transverse oscillators are physical states. So we have completely explicit natural representatives for the physical states. And here they are. Okay, at level 0, not much changes. We have the tachyon scalar for the open string. At level 1, we have a massless state, and we see here, yeah, we get exactly the transverse d-2 degrees of freedom of a photon. That's fine. And then at the massive level, okay, we get light cone states, meaning that we get representations of the transverse rotation group. And there's two types of representations. Actually, the symmetric tensor is reducible, so we have also to take out the trace. But for massive states, of course, the little group is a full rotation group. So what we then need to do, once we have written down these inequivalent physical states, is we have to put them together into representations of the full rotation subgroup. But this we can do easily by just using the branching rules that I explained last time backwards. And branching rule, which suggests itself, is to look at a symmetric traceless tensor of the full rotation group, reduce it out with respect to a transverse rotation subgroup, and then it precisely gives you the content that we have found in our light cone scheme. In 4 dimensions, such a state would correspond to a massive spin 2 particle. It's a 5-dimensional representation of SO3, so spin 2, also 5-dimensional representation, where the 5 states then correspond to the 5 possible projections of the spin onto a given axis with values between +2 and -2. Now, this gives me also opportunity to talk a little bit about why alpha prime is called the Regis slope. So let's stay in 4 dimensions and observe that the rank n symmetric traceless tensor is the spin n representation. And in the open string spectrum, we can always, if we are at level capital N, obtain a spin n representation by taking exclusively alpha minus oscillators. So this is the highest spin state at any given mass. And what one now does, well, what one now can do is draw a diagram of mass squared against spin. And again, I've drawn this, so I will want to show this to you. Here it is. So here we draw m squared on one axis and the spin on the other. And the possible values that we have in the string spectrum are these points. The formula is given here. Alpha prime is the slope of the lines that you find in this diagram. That's why it's called the Regge slope. And the line where you have the highest spin representation is traditionally called the leading Regge trajectory. So this is the one for the possible values of, if you're at level capital N, the possible values of spin is n minus n down to 0. And this here is then the leading, so-called leading Regge trajectory. Yeah, that this relates to the history of string theory. So string theory started out in the 70s or maybe even 60s as a theory of strong interactions. At that time, people were worrying about the so-called particle zoo. They knew that there were about 100 different hadronic particles, and they were trying to make sense out of it. And one of the structures that was observed is that the spectrum roughly fitted on such trajectories. And then the way it proceeded is that people tried to find scattering amplitude, which would be consistent with such a spectrum of states. This was then the famous Veneziano amplitude, which allegedly he found by browsing through some math books. And then other people came, I think Nambu in the first instance, and pointed out, well, the scattering amplitudes can be interpreted as the scattering amplitudes of strings. And then for some time, string theory was a candidate for a theory of strong interactions. This ended when experiments at higher energy became available, and one realized that the amplitudes that one gets from string theory behave too softly at higher energies. At higher energies, people then started to see the so-called photons. They realized that inside hadrons, you have hard particle-like constituents, which we nowadays call quarks. And so string theory disappeared, but because of this nice soft ultraviolet behavior, it was reborn as a theory of quantum gravity. And by another strange twist of history, it has lately reoccurred as a theory of strong interactions under the heading of the ADS-CFT correspondence, or more generally the gauge gravity correspondence. But this is now a different framework where you would postulate or argue for an equivalence between a gauge theory in 4 dimensions and a supergravity or string theory in 1 dimension higher. But we don't have time to digress into this direction. So still, I found this an appropriate point to make this historical remark. Now, light cone quantization. So what one has to do in this quantization program is to verify that the Lorentz algebra acts properly on the Hilbert space. In general, we will see there's an anomaly, and the quantum theory would not be Lorentz covariance, but we will see explicitly that this anomaly vanishes, if the dimension is exactly 26 and if the normal ordering constant is exactly a equals to 1. And we will even give a second independent proof of a equals to 1 by computing the shift in the ground state energy using the so-called zeta function regularization method. So I told you we solve the constraints Ln equals to 0 classically and get operators alpha minus as infinite sums over the alpha i's. But as we discussed previously, once we proceed to the quantum theory, we will have a normal ordering ambiguity. And as before, since this only applies to the operator with m equals to 0, I've parameterized this in the form of a constant a. Now I want to check Lorentz invariance. The Lorentz generators, if you first write them down, involve all possible alphas. Okay, the alpha pluses we have set equals to 0, but now we write our Lorentz generators in terms of light cone coordinates. Then we have also mixed Lorentz generators Li minus. And if the Lorentz algebra holds, then commutators between such operators must be 0. But if one does a computation, which is slightly lengthy, one finds it's not general, it's in general, because the alpha minuses are now quadratic, normal ordered in quadratic sums in the alpha I. So the computation becomes slightly messy, but if one suffers through, one finds that in general the result is some sum of operators with some coefficients. And now if you look at these coefficients, you realize if you want to have Lorentz invariance, and these coefficients must be 0 for all possible values of m, but the only way this can happen if d equals 26 and a equals 1 independently. So that's how you can derive full direct, but slightly painful way if you do the computation to get these results. Okay, now finally, let me also give you a different explanation why a, the normal ordering constant, must be equals to 1. This comes from comparison with the harmonic oscillator. So here's a standard harmonic oscillator with frequency omega in units where h bar equals to 1. I've put the creation annihilation operators in boldface so that we don't mix them up with the normal ordering constant a. The light cone Hamiltonian for an open string is an infinite sum over such harmonic oscillators, which we can make explicit by scaling out an appropriate factor of square root of n. Then we see that these are harmonic oscillators where the frequencies are integer valued if you set h bar equals to 1. And of course, there is, apart from the sum over all different frequencies, a sum over all the transverse dimensions. Now, if we take this Hamiltonian and split off the ground state energies, then the normal ordered part is a number operator restricted to transverse excitations. And the normal ordering constant adds up all these n over 2s. And this gives us a 1/2. The sum over transverse dimensions, which give us a d over 2. And then what we remain with is the infinite sum over all positive integers. This is, of course, a divergent sum. But there's one way to assign a unique and well-defined way a finite number to this divergent sum by making the following observation. Let us look at a more general sum, the sum over 1 over n to the power s, which for s equals to -1 is the sum, divergent sum that we want to assign a value for. We now realize that the sum converges for complex s as long as the real part of s is larger than 1. In fact, real part of s equals to 1 is the harmonic series, which we know diverges, but we also know that if we have a slightly higher power on 1 over n than the first power, then the series starts to converge. That means that for real part s larger than 1, we can define a function, zeta of s. And this function can then be analytically continued to the whole complex plane. It's a meromorphic function called the Riemann zeta function. And this function is in fact holomorphic except for the simple pole at s equals to 1, which corresponds to the harmonic series. But since it is holomorphic anywhere, I can use this to give to this sum for any value of s different from 1 in a unique, well-defined way, a finite value. This is then called the zeta regularized sum. So the zeta regularized sum is by definition evaluation of the Riemann zeta function at the corresponding point s. And if we do this in particular for s equals to -1, we have to evaluate zeta of -1, which gives -1 over 12. And by multiplying this with d over 2, we get -d over 24, which is, if you look back equivalent to saying that the normal ordering constant A is equal to 1 if we put D equals to 24, which is the value for the number of transverse dimensions that we get from imposing Lorentz covariance. Okay, this was really on the dot, precisely my alarm clock got off at this point. So that was then exactly part 5 for today's lecture. So you have available the corresponding example sheet already. And in the last lecture next week, I will talk about an advanced topic, namely compactification. So we have now realized that a consistent quantum theory of strings requires a higher number of dimensions than we observe. The number comes slightly down if you add fermions to the theory, to the value d equals to 10, but the principle remains the same. We need to learn how we can construct string theories which effectively have 4 dimensions, or one might say 4 large observable dimensions. And that will lead to a few very interesting new features. In particular, we will see that we've already seen that we can have a photon-like state, so U1 gauge group, but in particle physics, we also have non-abelian gauge groups, and we will see that if we have extra dimensions, if we curl them up, even in the simplest possible way as a torus, we will be able to get non-abelian gauge groups. And time permitting, we will also talk about T-duality, which tells us that if we curl up a dimension on a circle, then we can't tell a circle from a circle of inverse radius measured in string units. That is an equivalence between large and small scales in string theory, and somehow suggests to us that string theory has a minimal length scale that it can solve, namely the scale set by square root of alpha prime, the string scale. Okay, that's the sneak preview for next time. Thank you for joining today. And I'm looking forward to seeing you in a week's time for our last lecture. As usual, I will hang out here until you have all left, in case somebody has a question. Otherwise, goodbye and have a good week.